For years, artificial intelligence possessed vast, almost incomprehensible knowledge inside servers and supercomputers, but it was completely paralyzed in the physical world. The reality outside the screen was simply too chaotic for early models to navigate. Engineers initially tried to solve this by writing millions of lines of rigid code, but traditional programming collapses the moment a robot steps outside a controlled lab. You cannot manually code for every unpredictable variable, every dropped tool, unexpected shadow, or uneven surface in a real environment. To learn how to handle those variables, AI needed physical training data, but moving a real, heavy piece of metal is slow, expensive, and dangerous. That bottleneck kept industrial robots trapped in cages, repeating exact, pre-programmed motions in total isolation. By early 2026, a new architectural approach allowed these systems to break out of those constraints. AI models stopped merely learning executable commands and started interpreting physical reality in real time. Breaking AI out of its digital vacuum required solving the physical data bottleneck first. They needed a way to train robots without relying on the slow, expensive movements of the physical world. The solution was to abandon real-world physical training entirely. Instead of physical trials, developers built hyper-realistic virtual physics engines. Systems like NVIDIA's Cosmos 3 operate as world foundation models. Their specific engineering purpose is to close the visual gap between a flat, simulated environment and the chaos of an actual factory floor. The model translates abstract synthetic physics trajectories, basic coordinates, and joint angles directly into photorealistic video sequences. It then adds realistic lighting, material textures, and environmental noise over those trajectories. The robot's vision system learns to process glare or dust as if in a physical room. At scale, millions of virtual robots can fail, correct themselves, and learn simultaneously. This parallel processing generates massive datasets overnight. Using that data, forecasting tools like Cosmos Predict 2.5 can anticipate future world states up to 30 seconds ahead. The AI learns how a physical object will behave before it even makes contact. This synthetic training pipeline bypasses hardware wear and tear. There are no broken gears, no drained batteries, or slow human resets required during the learning phase. By mathematically resolving the differences between the digital and physical realms, these models close the sim-to-real gap. The software is deployment-ready before it is downloaded into a machine. By failing millions of times in simulated environments, AI systems amass lifetimes of physical experience before they touch a real piece of metal. With the training data secured, those digital minds are now being downloaded into physical bipedal humanoids on active factory floors. The deployment relies on vision-language-action, or VLA, models. Figure's Helix 02 operates as a prime example, a single, unified neural network controlling a robot's entire body simultaneously. Older systems required multiple layers of code to translate what a camera saw into how an arm should move. The VLA architecture wires raw camera pixels directly into physical joint torque, bypassing manual programming translations. This direct pipeline enables continuous, high-rate control of the entire physical structure at once. It is how these machines maintain fluid locomotion and balance while handling varied objects. Handing over that much torque to an autonomous system requires strict safety guardrails. Research frameworks like Google DeepMind's AutoRT manage this using a robot constitution. This constitutional layer acts as an internal filter for the system. It forces the underlying language model to self-reflect on its own capabilities, the environment, and strict safety rules before it attempts a task. If an action violates the rules, the robot rejects the prompt. Physical autonomy relies on a single integrated mind, one capable of perceiving its environment, reasoning through its own physical limits, and adjusting its torque in an instant. In 2026, these research architectures transitioned into massive commercial deployment. Tesla recently announced the cumulative production of over 50,000 Optimus units, integrating them directly into the industrial workforce. The hardware and software sectors are rapidly merging to support this scale. Boston Dynamics partnered with Google DeepMind to bring foundational intelligence models into their fully electric Atlas platform. These deployments mark a clear historical transition. The industry is moving away from specialized industrial tools locked in cages and toward generalized autonomous agents capable of unstructured labor. We are now outsourcing heavy physical lifting to titanium and silicon. The physical intelligence, once trapped in servers, is now walking factory floors. As machines take on the physical weight of the global supply chain, it forces us to define the new purpose of human labor in a physical AI economy. Thanks for watching. If you want to keep tracking these developments in robotics and AI, make sure to subscribe, and we'll see you in the next one.